So we're going to continue section 3.1 for college algebra. We're going to be talking about domain. Now you're going to want to mark this page because we're going to need to come back to domain lots of times throughout the entire rest of the class. For right now, we're just going to have two things that we have to watch out for. One of the things we have to watch is when we have variables in the denominator. I mean, having a denominator is not a problem, but if you have variables in the denominator, we have to be careful. The reason for that is because we don't ever want to divide by 0. So remember when we said NO dividing by 0 is undefined. So you can't divide by 0. So what we're going to do is we're going to find our domain restrictions by setting that denominator not equal to 0. So that's going to tell us what to avoid. So it's not telling us what our domain is, it's telling us what our domain is not. So find domain restrictions by setting the denominator not equal to 0. And then that's going to tell us like x cannot equal 4, for example. So that's what we have to avoid hitting. Then the other time is when we have variables inside even index radicals. Because remember when we look at complex numbers, like if we do the square root of -4, that gives us 2i. And primarily we're going to be working with real numbers. We will eventually also work with complex numbers, but when we're graphing functions, we want to stay in that real number system. So just having an even index doesn't mean we have domain restrictions. It's when you have variables in there. So the way that we overcome that is we are going to actually find the domain. So this one tells us the domain, not what to avoid. It tells us what we can be. And the way that we do that is by setting the radicand, which is what's inside the radical, so that it has to be positive or 0. So we say greater than or equal to 0. But for now, I mean, we'll come across other domain concerns later, but for right now, we only have those two things. If we don't have either of those two things, then all of our other functions have a domain of all real numbers, which in interval notation is -infinity to infinity. So when you are looking at a function, check for those two things to be going on. If you have variables in your denominator or variables under an even index radical, then you need to find your domain or find your restrictions. Anything else is all real numbers for the domain, -infinity to infinity. So let's look through some examples. You'll notice some similarities between these two here. So we'll get to those in a minute. The first one we're going to look at is this guy. We have f of x equals 3x over x plus 5. So when we see this function, I'm thinking, here I have variables in the denominator. And my strategy when I have variables in the denominator is that I take that whole denominator, x plus 5, and I set it not equal to 0. Then when I subtract that 5 over, I get x cannot equal -5. So if you think about a number line, on a number line, I would have all of my numbers going from -infinity all the way over to +infinity, except I can't equal -5. So I have like an open circle at -5 where I can't equal, but everything else is a part of my domain. So on a number line, that's what that domain would look like. In interval notation, I have two intervals, so I have to have, like I have two shaded regions, so I need two intervals. The first interval starts at -infinity and ends at -5, but it doesn't include -5. And then the second section starts at -5, ends at infinity, but doesn't include -5. So in interval notation, the domain would go -infinity to -5, not including negative 5, then union, because I'm skipping over something, start back up at negative 5, and go to infinity. In set builder notation, remember that's the one that goes curly brace x such that we just say x cannot equal negative 5, like that. All right, next one here. F of x equals square root of 3x minus 2. So again, we have even indexed radical, because that's a 2 on a square root. So what we need to do, our strategy for that, when we have an even indexed radical, is to set the radicand, which is the stuff under the radical, 3x minus 2, set it greater than or equal to 0. So we add that 2 over, 3x is greater than or equal to 2, divide by 3, x is greater than or equal to 2/3. On a number line, that would put us at 2/3, which since it's greater than or equal to, it's a closed circle at 2/3, and then greater than that. So that would give us interval notation, one shaded region, so one interval. We would go bracket, because we're including 2/3, 2/3 to the arrow over here, which is infinity. In set builder notation, curly brace x, so the set of all numbers x such that x is greater than or equal to 2/3. But now we have this guy here that has two things going on. It has a denominator and an even index radical, both happening at the same time. So we have to kind of combine those two ideas. So for the denominator part of it, remember we take that denominator and say it cannot equal 0. So if I square both sides, then I would get 3x minus 2 cannot equal 0. Add that 2 over, 3x cannot equal 2, and then x cannot equal 2/3. And then we just saw the radical from the radical. So this guy was from the denominator. Can't equal 0. And then this guy's from the radical, that the radicand has to be greater than or equal to 0. And we just solved that up there. So I'll kind of shortcut it and say that we got x is greater than or equal to 2/3. So we have two things happening in this problem at the same time. We have x is greater than or equal to 2/3, but then x cannot equal 2/3. So if you put those two ideas together, then that's going to tell me that instead of having that closed circle at 2/3, I have to have an open circle at 2/3. So when I combine those two restrictions, I go from 2/3 with an open circle to infinity. So that just changes my domain from a closed bracket to an open. So 2/3 to infinity would be my domain. And then in set builder notation, the set of all values of x such that x is just greater than 2/3. So watch out for that when you have more than one restriction that you have to pay attention to in your function. Okay. More on that here. Y equals square root of x plus 2 over x plus 5. Okay, this is like y is another way of saying f of x, right? It's just not function notation. So we still got to watch out for those restrictions. Here we have a radical with an even index, and here we have a denominator. So we're going to put those ideas again, put them together the same way that we kind of did before. So from our denominator, we get x plus 5 cannot equal 0, because that's our strategy. And that gives us x cannot equal negative 5. Then from our radical, we just take the radicand, x plus 2, that has to be greater than or equal to 0. So x has to be greater than or equal to -2. Let's look at a number line here. So here is -5, and here is -2. Now this part of our domain, x is greater than or equal to -2, would go -2, including, and then greater. And then x cannot equal -5. That's going to be open circle at -5, and then everything else would be included. So when you have these two things happening, it's like this the blue domain restriction allows the domain to be anywhere except for -5. So it's like that one friend that's like, okay, you can go anywhere you want, just don't go to one specific location. So this blue line can go almost anywhere. The green one has more strict parents, and they're like, okay, you can only go like north of 15th Street, whatever restriction they have. So if the two friends want to hang out together, the green friend is not allowed to go over here. So if the blue friend wants to hang out with the green friend, then they're going to have to restrict to this location so they can hang out together. So the overlap is what we're looking for the domain. In this case, our domain is going to be from -2 to infinity, because that's where they're both allowed to hang out, and it's going to be a closed circle since they're both allowed to be at -2. So if we were looking at set builder notation, that would be the set of all values of x such that x is greater than or equal to -2. Now this function is slightly different. From the radical is still going to be the same. So from the radical, we're still getting that x has to be greater than or equal to -2, because that's the same as that problem was. But now from the denominator, we had x minus 5 cannot equal 0, so x cannot equal 5. Okay. So let's look at that on a number line. A little bit different, but kind of the same idea. So I guess we need now -2 and 5. X cannot equal 5 is going to, again, be like open circle at 5, but they can go anywhere else. And then greater than or equal to -2 goes at -2, and then to infinity like that. Okay. So now, again, we want the blue friend and green friend want to hang out together. The green friend is allowed to go still anywhere like north of 15th Street. But now the blue friend is like, okay, you can go anywhere except for, I don't know, what's north of 15th Street? How about like the Casey's there on the corner? So if they want to hang out together, they have to stay north of 15th Street, but then they're also not allowed to go to Casey's. So now we have from -2 up to 5. I can't go to 5, and then I can start again after 5. Okay, so on that domain, when we overlap those, we can start at -2, and we're both allowed to be at -2. But then when we get up to 5, we have to cut out 5. So that's going to be an open circle or a parenthesis. And then we can pick back up after 5 and go to infinity. So that would be that domain. In set builder notation, it's a little bit more complicated. We would have the set of all values of x such that. So the shaded part represents the x. So it's trapped in between -2 and 5. So x is trapped in between -2 and 5. X is bigger than or equal to -2, but x is smaller than 5, but not equal to, because it's got an open circle. Or we have this part of it, x is greater than 5. Okay, what about this guy? Y equals x plus 4 over x cubed minus 4x. So now our domain concern, I see things in the denominator. I see variables in the denominator. So when there's variables in the denominator, remember we take that denominator, x cubed minus 4x, and we set it not equal to 0. And then we're going to solve. So to solve this, I'm going to start by taking out a GCF, which is x, and that leaves me x squared minus 4 cannot equal 0. And then I can factor this by difference of squares. So I'm going to have x times x plus 2, x minus 2 cannot equal 0. Then I use the zero product property that says if I have things multiplied together and the product is 0, then either x has to equal 0, or x plus 2 has to equal 0, or x minus 2 has to equal 0. So that gives me that x cannot equal 2, -2, and 0, all three of those. On a number line, then, I have negative infinity to infinity. I have -2, 0, and 2. And I can't equal -2, I can't equal 0, I can't equal 2, but I can be anything else on that number line. This is where things get a little bit complicated on interval notation, and people tend to forget some of the intervals. Just remember that each time you see a shaded section, you need to have a separate interval. So I have 1 shaded section, 2 shaded sections, 3 shaded sections, 4. So 4 shaded sections means I need 4 intervals for my domain. So I'm going to go, the first one will go negative infinity to -2, skip over -2. And then the next one will go -2 to 0, skip over. The next one will go 0 to 2, another skip. And finally 2 to infinity. Interval notation is more complicated on this one. Set builder notation is a bit easier because I can just say all the values of x such that x is not equal to 0, -2, and 2. And I'm not sure if my math lab would let you just do x can equal 0, 2, -2 like we did up here, or if you'd have to put all of that out there. You guys will have to figure that out and let me know because I'm unsure about that. When we combine functions, the domain of the combined functions is the domain of each inputted function, which is the overlap of the two domains. So we have to look at kind of 3 things. We have to look at each of the original restrictions and the domain of the final function. So now we kind of add another level of complication here. This symbol is the intersection. So it's where they cross over. So we need to look at the domain of the original function, the original 2 functions that we're combining, and we have to look at the domain of the final function to see where we're at. Actually, I'm going to pause this and go double check because sometimes some programs only look at the ending function for domain. So I'm going to double check on that and be right back. Okay, I checked on that, and that is how the MyMathLab handles it in the college algebra textbook that we're using. So when we combine functions, like when we add them, subtract them, multiply them, or divide them, we're going to look at the domain of each individual input function, and then at the end, we're going to look at the final function, and we're going to get that domain all together. One thing you have to watch out for when you're doing the dividing is that you're introducing a new domain restriction because when you started out, f of x and g of x were not in denominators, but when you do the dividing, now they are. So you have to watch out for this. So you have to restrict the domain so that g of x is not equal to 0. So we're going to want to watch for that. Okay, here we've got f of x is square root of x minus 1. G of x is square root of 4 minus x. So we're going to start out by finding the domain of each individually, and then we're going to do some combining and look at the domains. So for f of x, we know that that's in an even index radical. So we take the radicand, set it greater than or equal to 0, which gives me x is greater than or equal to 1. And then if I look at g of x, which is 4 minus x, inside an even index radical as well. So 4 minus x is greater than or equal to 0. If I add that x over, that gives me 4 is greater than or equal to x, which if I switch it around is x is less than or equal to 4. Remember that if you switch the sides of an inequality, you have to reverse that symbol. So they're asking me to find f of x plus g of x. That's what this means. F plus g of x means that we're going to do f of x plus g of x and then find its domain. So our first function was f of x, square root of x minus 1. And I'm going to add to that g of x, which was square root of 4 minus x. And then the domain of the resulting function. Okay, so let's look. So this guy we had 1, and this guy involves 4. So my f of x says x has to be greater than or equal to 1. So here to the right. G of x says x has to be less than or equal to 4. And then when I add those two functions together, then they need to hang out, So the green function's only allowed to go to the right of 1. The blue function's only allowed to go to the left of 4. So if they want to hang out together, they're going to have to stay in that zone here where they both are allowed to be. So the domain of the overlapping function is just going to be here in between 1 and 4. So we'll have 1 to 4, including both of those end pieces. If we needed that in set builder notation, we'd say all the values of x such that x is trapped between 1 and 4. And it's including both, so we go in less than or equal to. So x is greater than or equal to 1 and less than or equal to 4 at the same time. Okay, this starts a new problem. Probably should have put a line there so it's not confusing. All right, x squared minus 2x for one of our functions and square root of x for the other function. Let's see, this f of x does not have any variables in the denominator, does not have any variables under an even index radical, so its domain would be all real numbers. It's allowed to go anywhere. And then g of x, of course, is under a radical. So being under a radical, we set that radicand greater than or equal to 0. So x greater than or equal to 0, which is already solved already. So the domain would be 0 to infinity. If we look at just the overlap of those two domains, let's see, 0 is the only important number in there. The f of x function is allowed to go anywhere. The g of x function is only allowed to go 0 to infinity. So any functions that we combine together already can only go from 0 to infinity. So any of these functions I combine, the combined domain is going to be 0 to infinity. Of course, we also have to watch out for the ending function to make sure there's no other restrictions that are added into the problem. Okay. So f of x plus g of x. We'll have x squared minus 2x. We're going to add g of x, which is square root of x. Nothing can be combined within these two functions. So that's all I'm going to have for my function. And then the domain, I've added no new restrictions. So I'm just working with the combined domain of 0 to infinity, including 0. Now on g minus f of x, so that's going to be g of x, and we're going to subtract f of x. When you do this combining of functions and you have subtraction, I want you to always put your second function in a set of parentheses, always. If you don't do that, you'll probably make a sign error along the way. So we're going to take our f of x, g of x, which was square root of x, and we're going to be subtracting f of x, which was x squared minus 2x. And I want to make sure I get that second function inside parentheses, because that's going to remind me that that subtraction applies to all of those terms. So when I combine those together, then I have square root of x minus x squared plus 2x. So that's going to be my combined function, g minus f of x. As far as domain restrictions on the ending function, this is the only thing I'm seeing, which matches the original input functions. So the domain for this combined function will also be 0 to infinity, including the 0. F times g of x. So that means we're doing f of x times g of x. And you're going to want to watch parentheses on this one as well. Just if you have more than one term, you need to put it in parentheses so you remember to either distribute or FOIL. So my f of x was x squared minus 2x. I'll go ahead and use parentheses with it. And then times g of x, which was square root of x. Now I can distribute that square root of x. So I'll have x squared times the square root of x minus 2x times the square root of x. And then looking at any additional domain restrictions, the square root of x is the only thing I'm seeing. So that domain would still just be 0 to infinity, including 0. If you wanted to leave your answer like this with the square root of x outside the parentheses, I don't see any problem with that either. Okay, f over g of x. That means we're taking f of x and dividing it by g of x. So my function f of x was x squared minus 2x, and g of x was square root of x. And remember what we had said at the top. When we're doing these divisions, we have to watch that new domain restriction. So we have added a new domain restriction because we put a variable in the denominator. So when we have variables in the denominator, remember that we have to set that denominator to not equal 0. So we have to watch that the square root of x cannot equal 0. And when you square both sides, you get x cannot equal 0. So now instead of our domain including from 0 to infinity, we've now added that x cannot equal 0. So the domain on this combined function would be from 0 to infinity, not including 0. Now let's look at g over f of x, which will be g of x over f of x. So we're basically just flipping this upside down. So we have square root of x over x squared minus 2x. Okay. And again, there is a new domain restriction. So I need to use my denominator strategy, which is to set the denominator not equal to 0, like we did up here. And when we solve this, we're going to need to factor. So x times x minus 2 cannot equal 0. So now I am getting x cannot equal 0 from here, and x cannot equal 2 from that one. Okay, so back up to my domain. So now I have to avoid 0, but I also have to avoid 2. So on that number line, I had 0 to infinity from my original. So here's 0, here's 2. 0 to infinity from my original, combined of the two functions. And now I'm also including x cannot equal 0, x cannot equal 2. So when I look at that overlap, I'm going to have to stick between 0 and infinity, but I'm not going to include 0, and I'm not going to include 2. So my combined domain will not include 0, not include 2, but go to infinity like that. So I have two shaded sections, which means that my domain is going to have 2 intervals. So the first interval will go from 0 to 2, not including either number. Then I have that union, because I'm skipping over 2, and going to infinity. I can also ask you to do f plus g of a number instead of f plus g of x. And so that's just asking you, instead of doing f of x, we're doing f of 25 plus g of 25. And of course, that means that we're going to take the function f and replace our variables with the input of 25, and then take the function g and replace our variables with the input of 25 and work through that. So we can just do that pretty easily. Let's see, f of x was x squared. So I'm going to replace my x with 25. So I have 25, and I'm squaring that because the original function was squared, minus 2. Instead of minus 2x, it's minus 2 times 25. And then I'm adding to that g of 25. G of x was the square root of x, but instead of square root of x, I'm replacing that x with the input of 25. So square root of 25. And then I just work through that. Okay, so 25 squared is 625. Minus 2 times 25 is 50, plus square root of 25, which is 5. Let's see, 625 minus 50 would be 575, plus 5 would be 580. All right, now let's look at a graph. So we're going to be combining functions and evaluating functions from a graph. So we've got f of x and g of x. So I'm just going to color these so that it's a little bit easier. Darn it, I colored the wrong one, the wrong color. It's fine, we can work with it. So g of x is going to be our orange function, and I'm going to make f of x blue. Now you see that there's like some fat dots on this graph. Well, that's just for emphasis. Like, there are a million, billion, infinite number of ordered pairs on these graphs. Some of them are like, I made them like fat dots so that I would make sure that I hit those particular values, but that doesn't make them any more important than any other dots on the function. It's like f of 5 still exists and it has a value, even though there's not, a thick dot there. It's fine. Just don't be thrown off by having some of the dots be thick dots and others not. You could just, like, don't let that throw you off. Please, please, please. So let's look at our domains. So the domain for f of x if we scan our graph left to right, the function starts at -3 and is continuing all the way until x is 8. So that domain for f of x would be from -3 to 8, including both endpoints. For g of x first starts at -4 and its last x value is 6. So -4 to 6, including both. Now, when I start looking at the combined domain, I need the overlap. So on my overlap, remember, I can only hang out where we both are allowed if we want to be together, if we want to hang out together. So blue and orange can only hang out between -3 and they stop here at 6. That's the only places they're overlapping. So I could not ask you to do f plus g of 10 because neither function hangs out there. I also could not ask you to do f plus g of 7 because g of x doesn't exist at 7, so it does not make any sense to add them together. So the domain of the overlapping functions, f plus g, would be from -3 to 6. All right. Let's look at evaluating f plus g of -3. So what that's asking me to do is find f of -3 and add that to g of -3. So what does f of -3 mean? F of -3 means the y value when x is -3 on the function f of x. So if I look at f of x, when the x value is -3, what's the y value? The y value is 1. That's not supposed to be there. So -3, 1. I'll rewrite that. That's weird looking. Okay, so f of -3 is 1. So I can replace f of -3 with 1 plus, and then g of -3, I'm looking on the g of x function for that ordered pair, and I need the y value when x is -3. So -3 is 0, -3, 0. So g of -3 is 0. So f plus g of -3 ends up being 1. Okay, let's look at some more. F minus g of 8 means that I need to take f of 8 and subtract g of 8. F of 8 is the y value when x is 8. So I go to x equals 8. It's 1, 2, 3, 4. So f of 8 is 4. And g of 8, well, g of 8 doesn't exist. So I can't really do 4 minus does not exist. So this would be no solution because it's not in the domain of my combined function. -3 to 6, so 8 is not in the domain of that combined function. So no solution. Okay. F times g of 0. F times g of 0 means we need to find f of 0, and we need to find g of 0, and then we're going to multiply those. So remember, f of 0 means what is the y value when x is 0 on the function f. So x is 0, y value is 2. And then g of 0 means what is the y value when x is 0 on g of x. So x is 0, g of x is -2. So when I do the multiplication there, 2 times -2, I get -4 for that answer. Okay, let's look at this one next. F over g of -3. So that means we're going to be doing f of negative 3, divided by g of negative 3. So if we look on our graph, remember f of negative 3 means when x is negative 3, what is the y value on f of x? So when x is negative 3, the y value is 1. And then g of negative 3, when x is negative 3, what is the y value? It is 0. So we're asking it to do 1 divided by 0. And remember that that is a no, so that is undefined, or no solution on that one. Let's reverse it. If g of x equals 0, find x. So this is asking me, this is a y value. If g of x equals 0, find x. So I am looking for ordered pairs on my graph that would have some x value and then 0 for the y value. And my answer is going to be what x equals when y is 0. So y is 0, 4, 3, 2, 1. Y is 0 anywhere along here, because like this is the ordered pair, 1, 0, 2, 0, 3, 0. So where would g of x be along y equals 0? So I've got one here at x equals 3, and I've got another one here at x equals negative 3. So my x values are negative 3 and 3. Now, if they were asking me for f of x, those would be like 4 and 7. What if they asked me to find the x values when f of x equals 1? So here's f of x. Here's the y value of 1. So f of x equaling 1 means the y value equals 1. So I would be answering x equals 2 and negative 3, and then there's another one over here at like maybe 7.5. Even though there's not like a thick dot there, it's still there. There's still a value there, so 7.5. Okay, what's the domain of f over g of x? So we already know the combined domain for f of x and g of x, but when we put f over g of x, that means we're doing f of x over g of x. Remember that that's introducing a new restriction. That new restriction is that g of x cannot equal 0. So we now have to include g of x cannot equal 0. And our g of x function, we don't know the function, but we know where g of x equals 0. We just did that. G of x equals 0 when x equals negative 3 and 3. So we have to say that x cannot equal negative 3 and 3. So let's look at that compared to, well, I guess combined with the domain that we had already restricted. So our combined domain was negative 3 to 6. So we've got negative 3 is important, 6 is important, and now 3 is also important. So let's get all of those on there. With my combined function, we had negative 3 to 6, including both. So here was my combined function. And now, with my new restrictions, it's telling me x cannot equal negative 3, x cannot equal 3. So these restrictions cover all of that. But remember that we're combining these functions together, so we can only be where everyone's allowed to be. So we go, we got a limit to in here because the pink goes outside of those borders. But then we also have to exclude negative 3 and 3. So when I combine that all together, my combined domain is going to go here, open circle at negative 3, across to here, another open circle at 3, across to here, and a closed circle at 6. So I have 2 sections, which means I need 2 intervals. So that domain would be open from negative 3 to 3, skip over 3, and then open at 3 and go to 6, but it's closed at 6.